Hello and welcome. In 2 days I'll be giving a talk in a blockchain conference in Munich, in the Technical University of Munich. And I just finished making my slides, and this is a dry run of my presentation that I'm doing for my own practice, but I thought I would also record it to publish it. Fun fact, this is the second time I'm doing this. The first time, unfortunately, I think I did a pretty good job, but my recording software just crashed. So this time I'm trying Loom, hopefully it'll work. Alright, so my name is Kian. I'm an engineering lead at Parity Technologies and a member of the Polkadot Fellowship. I've been contributing to the development of Polkadot protocol for around 6 years now. And I stand here today as a prelude of my talk to confess that I increasingly feel a sense of purpose dysphoria in this ecosystem. In that we are building more and more technology, ever more grandiose, ever more buzzwordy. But I think perhaps we have lost sight of what were the core principles and use cases for which we started to build. So this has encouraged me to embark on a journey to unlearn a lot of things about blockchains and relearn them again from scratch. Through this journey, I developed a simple mental model of how different approaches to blockchain scalability work. A lot of it is about rollups, so you're already familiar with that part of it. And this talk is a slice of this broader journey and philosophical question that I'm pursuing. The full writing of this quest would hopefully also become available sometime in the next few months. So that's that. And finally, I'm in an academic environment here in this conference. I won't really try to sell you any product or tell you which platform or blockchain you should use for your, I don't know, meme coin launch or whatever. I'm really trying to gain a grade of understanding that is useful for tackling macro problems in our space, such as answering the question of what is this technology really useful for? What is the next killer feature at a broad scale for this technology? So I'm really pursuing these kinds of questions, and I won't be going into too much of a, use Polkadot kind of thinking. So I'll try and be very, very unopinionated in that sense. Very much like an educator. All right. I have a little bit of intro that I need to establish before we can get to the actual scalability matter. Let's start with the age-old example of owning digital money. So I have 1,000 euros in a bank like Revolut, and I have 1,000 euros in a distributed system like Bitcoin. And how is it that I find both of them credible and noteworthy? So in the Revolut model, in theory, in principle, as little as one computer stores the actual information that I own this 1,000 euros. And when I want to go and make a transaction, send 100 of this to someone else, all I need to do is to communicate to this one computer. And why do we find this trustworthy and credible? It's things like governments, social norms, regulations, and at the very foundation of it, very often law enforcement, military. So this model scales really well, and its source of trust is as I explained. Then when we look at the Bitcoin network and we contemplate, well, why is it that I trust this 1,000 euros to exist in the Bitcoin network as well? We can conclude that this system is only credible and trustworthy because instead of those social norms or man-made structures that I talked about, we are synthesizing a new form of trust in the Bitcoin network, one that is based on a few branches of science, such as mathematics, computer science, game theory, and economics, or perhaps a few more. And these branches of science combined together give us the same or a very high degree of credibility and trustworthiness. And in the opinion of a lot of people who started this industry more than a decade ago, this type of trust was considered superior because it has this element of verifiability. Moreover, knowing this fact, these branches of science very often involve types of games that need to be executed by stake-backed validators in a network. In that, in a network like Bitcoin or Ethereum or Polkadot, there's a large entity, a large group of entities that we call them validators. These are people who take turn in being the temporary dictator, the temporary authority in the system, and propose a new outcome for the system and having everyone else check their work. So this property of like this redundant type of work that happens here is combined with these sort of things like economic security is the source of why we consider all of this stuff valuable to begin with. It's the source of why it's considered trustworthy. And the same redundancy, the same redundant nature of work is also the reason why these systems are so slow. So we can build this model where a distributed network like Bitcoin or Ethereum or so on is composed of many state-backed validators that are working in coordination, in synchrony of one another. And they cannot go and each do different work. They only process work in a sequential manner. Like one block of work, one package of work comes in, one of them will process it, everyone else would check it at a very simple abstract level. And in the Revolut model, this is really not the case because we don't have all these games of doing redundant work and then establishing this trust. So the reason for this introduction was to establish a mental model where we can see the entire validator set of a blockchain network like a very slow but trustworthy computer. And then the challenge that we have is, how can we make this computer go faster? How can we make it do more work? And the phenomena that happens, as we will explore, is that as we try to make this computer go faster, potentially some areas get compromised, and at some point this compromise might be around the economic security of the network, which kind of perhaps defy the purpose. But again, that's like the broader philosophical question here. For the rest of this talk, I would be only telling you the landscape of the different approaches to scale this single computer, this a computer that is composed of these validators. All right, so let's look at the options. The first one is the simplest one in that it doesn't really try and tackle anything at the architectural level. It's more about saying, okay, well, let's have these validators have sci-fi level hardware and as fast as they can be. Please juice it up with the best CPU and best RAM and best disk that you can do. So it's a mix of hardware requirements and software tricks such as parallelization and so on. And this system scales well. It also doesn't suffer from any kind of fragmentation because we keep the blockchain as it is. Like there's just one blockchain, it's just very fast, and therefore we can process more information. Solana is the main network that adopts broadly this strategy in that it doesn't try to fragment itself or create shards or whatever. The base principle of it is that we're going to have one very fast blockchain. And the concern that broadly exists here is that we should be careful that as we're introducing these optimizations, the optimization doesn't become cutting corners on the original principles of having a trustworthy system. So then the second model is analogous to saying, okay, we can have 1,000 validators secure one blockchain. Why not split that 1,000 validators into 10 buckets of 100 and have them scale 10 blockchains? I'm doing the same thing here, but with 3. This approach does achieve scalability, but it's implying that we're also sharding our amount of economic security. Because as you're aware, the amount of security that each of these blockchains derive is proportionate to the amount of capital that is staked in that blockchain, economic security. And it's not a desirable property to have a blockchain where we have less economic security in any condition. So if you fully shard your network, I call this a fully sharded multi-chain, you're also sharding your economic security. This is a model that was first advocated by the Cosmos ecosystem, especially in the original versions. I think nowadays with approaches like interchain security, they are revising that. But more or less, I think the Cosmos original model was like that. So the main characteristic, or the most specific characteristic of this approach is that we end up with systems that just have less economic security because we have fragmented our economic security as well. But even aside from this, this is the first model in which we are introducing something similar to rollups, something similar to splitting our blockchain into smaller blockchains, introducing a multi-chain narrative. And I want to bring your attention to some of the downsides of multi-chain networks as well. The first is that each of these blockchains have their own consensus, have their own notion of time, or what is my block progress, and so on, which means they cannot really communicate with each other in a synchronous manner. And this is what I'm trying to demonstrate here with this line and the fact that there's usually a bridge if they want to send a message, and this bridge could be very slow, it's asynchronous, and so on. It's also worth noting, implementing a fully trustless bridge is not an easy feat, and unfortunately most bridges out there are not actually fully trustless. More importantly, in such a system, because we have varying degrees of economic security, you end up with the possibility that the weakest link in this network can become the subject of an attack. So imagine you are a blockchain secured by $1 billion, and you want to send a message, or you want to receive a message from a blockchain that has $1 million and $100,000 securing it as in terms of economic security. Why would you trust that, right? Or why would you compromise by trusting this message that's coming from such a weak source of security? And when these messages contain things like, hey, I burned some ETH on my side, please mint it on your side, it's actually, you should think twice before executing upon it. So broadly speaking, when we have these systems that are fragmented and each fragment has a different level of economic security, this is another challenge that we have at our hand, that communication cannot be as seamless or cannot be as trustless, because when two parties are talking to one another, one could be significantly more secure than the other. All right, next let's talk about optimistic rollups. This is the most known paradigm as far as I understand. In this paradigm, we keep our base secure blockchain, which we now can call L1, just for the sake of using the same jargon and having familiar words. We can keep the validator set of L1 more or less as it is, as in we don't try to split them or bring any fanciness into them. And instead we say, well, instead of sending all this workload to these slow validators directly, let's process them off-chain and assume that this processing that's happening off-chain, aka in the L2, in the layer 2, is secure unless if proven otherwise. So the assumption is that the work being done here is benevolent, it's honest, unless if someone reports that there is a fraud happening. This is why in these systems we have this very important actors, fraud provers or fishermen, or generally speaking, there needs to be a process in which anyone can report a fraud, and most importantly, something that unfortunately is missing nowadays in the space, when a fraud has been reported, then the L1 validators need a way to then say, okay, who's winning? Who wins the argument? Who wins that fraud? And we can go and check these security parameters or the existence of fraud proofs at the moment in the website L2Beat, and it is unfortunate that a lot of the L2s don't have this yet implemented. That being said, optimistic rollups in the presence of fraud proofs are sort of, you can say, secure, because again, when there is fraud, and assuming that running a fraud prover is permissionless or it's not something that can be easily censored, we can be sure that if there is fraud, the same L1 validators will resolve it. Therefore, it's as secure in terms of economically secured execution as the L1 is. So, at the presence of fraud provers, it's a secure system. What else? This system scales pretty well because other than the need for data availability, as we have discussed so far, if a fourth rollup joins this group of rollups, it's no extra work really for the L1. As long as there's no fraud, it's like whatever, just do your work. we don't really care about you. So in terms of execution burden on the L1 validators, this is a pretty good model. It doesn't impose any limitations, so we can kind of imagine that the number of L2s can grow a lot in this model. It suffers from low finality because we have to wait for some window of time to say, okay, if a fraud doesn't come within 1 hour, 1 day, 1 week, 1 month or something, we kind of assume it's okay. And at the moment, as far as I know, something like 2 weeks is the norm there. So 2 weeks is a pretty long time to finality, especially if you're doing high value transactions, for example. And this system suffers from the same problems that the previous system also had, in that it's given that, at least at the moment at the implementation level, these L2s, some of them have fraud proof, some of them have excellent fraud proof, some of them have half-baked fraud proofs. They do have varying degrees of security, which means you have the weakest link problem. You generally have the security is not homogeneous. The degree of security differs. Therefore, when chains or L2s are communicating, they might potentially refuse to do that communication, or it's not safe for them to communicate to an L2 that is very insecure. Although, again, perhaps in practice we're seeing no one's caring about this, but it's one of those things that maybe only a black swan event can fix for us. They also suffer from the same fragmentation situation, that these L2s are sovereign separate blockchains, and if they want to talk to each other, they have to go through a bridge, so on and so forth. So it's a complicated situation there. All right, next I want to introduce you to a new type of rollup, which I would imagine you have not heard of before, and it's part of the new understanding that I would like to advocate in this talk, called cynical rollups. Cynical rollups can be best described in an introductory manner as similar to optimistic rollups, except that fraud proving happens proactively. A, it happens proactively. B, it happens by other neighboring validators that are as secure as all the other validators. So in this situation, we do involve L1 validators in the work. So let's start from here. The work happens on the L2 outside of the security zone, but this work is checked by some small subset of validators and then rechecked by another small subset of validators. And this property of doing this proactive checking allows us to assert that the security level of this L2 is as secure as L1. So in some sense, the L1 validators are not all re-executing all of the L2's work. Only a small subset do. And then another small subset recheck things. And which brings us to this property where, in the absence of fraud, the system is more or less execution sharded, as in not all validators re-execute everything, but security is shared because in the presence of fraud, or in the possibility of the fraud, this situation quickly escalates and involves all the validators to come in and check everyone's work. So it's kind of like this Hydra analogy, that if you cut one head, 2 more comes in. If one of the validators here tries to sneak in, 5 more jump in to check it, and very quickly this means all L1 validators are rechecking someone's work. This process is quite involved and beyond what I can explain here in 1-2 minutes. It's been recently formalized in a paper published by Web3 Foundation called ELVES, and I recommend you to check it out. It exactly describes why cynical rollups are a middle ground here, in that they achieve 2 properties that we previously considered are mutually exclusive: sharded execution, but security is shared. And again, the conclusion of this ELVES paper and this cynical rollup model is that the cost to perform a double spend on one of these L2s is in practice as high as the cost of performing a double spend on the L1. That being said, this proactiveness comes with a double-edged sword, in that the system reaches finality much faster because checking is happening proactively, but it is not as cheap as optimistic rollups, because the L1 validators are doing some little amount of work for you automatically, without even the possibility of fraud. So in that sense, it scales less. For example, I can say that in the cynical rollup is how Polkadot works under the hood. So I would get to that in a further slide. But in the Polkadot model with around 1,000 validators, we estimate we can have like 300 something rollups. That's like, just to give you an estimate. And then we have to think about how we can scale the validator set further. But needless to say, there are limitations to this approach, but it's much, much more secure. An analogy that I like to use here to demonstrate the difference between cynical rollups and optimistic rollups is that in the optimistic rollup model, there's a room full of validators, and you go in there and you just sit silently. And if after 2 weeks no one says anything is wrong, you leave that room and you assume everything is fine. In the cynical rollup model, you enter the same room, but you ask one random validator, what do you think? Do you think this is correct or not? And then you ask 3 more random validators, what do you think the first guy? Do you think the first guy was open? And if you do these games enough, you end up with this property where your L2s are as secure as the L1. All right, so that's it about cynical rollups. Let's also consider one other category of rollups. Usually they're known as ZK rollups, but I think it's more accurate to call them SNARK-based rollups, and I generalize it even one step further and call them asymmetric rollups, because they all, end of the day, from my perspective as like not a ZK, mathematician guy or whatever, they are all leveraging asymmetric execution in that they enforce the L2 to do a lot more work, to generate a very sophisticated proof, a very complicated proof, again, like SNARK-based mathematics beyond my head in all ways. In all possible ways, but they generate this very succinct proof that is difficult for the L2s to produce, but it's very cheap for the L1 to verify. And this is the asymmetry that I'm talking about. So you ask the L2 to do a lot more work, but the L1 can then easily verify it. So you can see similarly at the L1 level here, we have no fancy sharding or whatever. The L1, very similar to optimistic rollup model, is just working as it would work. And we don't really bother with scaling the L1 because verifying this proof is quite easy for the L1 validators. They can just do it in the traditional model of, everyone re-executes everything. This model is secure, as in, there's no ifs and buts to it. There's no need for a fraud prover. It's, if this proof is correct, it is correct. The same way 2 + 2 is 4. This rollups execution was correct because the proof said so. The main downside is this cost imposed on DL2. So kind of similar to the hyper-optimization model, the type of hardware necessary to be able to achieve this asynchrony, at least at the moment, seems to be very skewed. I think there's like, I don't know, let's say if you compare like the cost of executing an EVM contract versus executing it and generating this fraud proof, I think at least earlier this year, I read a report which claimed it's like generating the proof is like around, 560,000 times more expensive. So, there's like this huge extra amount of work that is imposed on these L2 block producers. And this could cause its own set of risks if that's the case. I think that this field is improving, but it's at the moment, I think, the main blocker. Similarly, I think the generality of these circuits that can generate these proofs is also still something that is evolving. So I think certain simple operations can be turned into a circuit quite easily, but any program, any execution is more involved. All in all, I can say ZK-based rollups, as they're evolving, they are very promising if they manage to overcome these 2 challenges, because they have this security part very much embedded into them. All right, and then I would need to inject a little bit of Polkadot terminology into my presentation, only because I need it before I can get to the last flavor of rollup that I'm going to introduce, which is Jam. So Polkadot uses the cynical rollup model. Basically, the cynical rollup model is the outcome of Polkadot's implementation. It's something that was formalized out of Polkadot. In the Polkadot model, we call this group of validators that do the checking for one of the L2s a core. And each of these L2s is called a parachain, a blockchain that runs in parallel to other ones. This model does not really suffer from the issue of communication being risky because the security level of all of these parachains is homogeneous. That's important to, or worth noting. I think in this slide also we can see that, that ninja emoji is missing, so I'm trying to imply that. The same fragmentation issue exists, so communication between two parachains is slow, it's asynchronous. And yeah, so that's a current situation. That's actually the Polkadot 1.0 model. At the moment, Polkadot is also evolving into its second version, which is all about making the usage of these cores more flexible. So in the original model, one of these parachains had to sort of make a contract with Polkadot or lease one of these cores for 6 months, 1 year, or 2 years at a time. Now it's like way more fine-grained. You can do it for a day, a week, a month. You can even do it on demand, as in you can be a parachain that only produces blocks or only goes to a core and does some work whenever there is demand for it, and if not, it's just sitting idle. We are also adding the ability to do the opposite, so elastically scale into multiple cores if necessary. So you're a parachain, you use one core all the time, but when you have a spike in your demand, you can use 3 cores. And finally, we're adopting or introducing lower block times. That's all to say, again, I don't want to necessarily pitch these features. It's all to say that Polkadot's evolution is going toward this fact that this cynical rollup model is powerful, it's good, and these cores are very powerful primitives. These execution sharded but security shared execution cores are powerful primitives, and let's make the usage of them more flexible. And we can already see this trend in Polkadot 2. But I want to take it even a step further, or introduce you to a system that takes this a massive step further, and this is Polkadot Jam. Polkadot Jam is like the next generation of Polkadot relay chain, which aims to take the same properties of cynical rollups and expose all of them to developers. So the Jam is in some sense like a gutting of Polkadot. It's like it's breaking all the assumptions and barriers. If we look at the cynical rollup model, we can interestingly see that we have this dualism. Some work happens inside a core, so it's like in this sharded land where you have a lot more throughput, and some work happens on-chain where you have like the utmost security. And then you have the data availability layer sitting in between. And all of these 3 components, crucially, are exposed to the applications that can be written on Jam. So as a developer in this paradigm, you're not bound to I am a blockchain and this is my rules. You have access to these primitives and you can write, you can use them as you wish. So in that sense, it's a step forward for the rollup space because it's exposing the underlying technologies that makes rollups possible directly to the developers of these rollups. And another property that I'm trying to explain by this jumbled set of lines that are grouping these work items, you can see there's no longer the sequence of blocks that are just like going into one core and it's kind of rigid. Jam imposes no opinion on which group of works have to be combined together and sent to a core at any given time. It's all flexible and is left to sort of like market needs and ad hoc algorithms or block producers to figure it out. And this means sort of L2s or applications that need to communicate with one another need not suffer anymore from this persistent fragmentation issue that we have observed so far. So let me rephrase it differently. Why do I think Jam is a big deal or a big step forward for the rollup space? All of the solutions that we have seen so far, they embed in this rigid opinion that different applications are blockchains and these are the boundaries of them. So the different L2s are all blockchains and here's the boundary, and this boundary cannot really change. Jam is in an interesting way and radically questioning this property, and that why those boundaries need to be rigid all the time. And again, all the little nooks and crannies and details that make this possible is beyond what I can fit here, but hopefully this previous diagram sheds light a little bit into why Jam goes into this direction. All right, I'm a little bit over my 30 minutes allocated time, so that's a good feedback for me to know. and moving myself up here. Let's have this quick recap of the different approaches that we have considered. So the hyper-optimized network, they are economically secured in principle, but they have to, the question that they need to answer, or they need to keep in mind, is that whether any of the core principles of creating these trustless systems is being compromised when we are adopting and deploying these optimizations. So this second axis of whether economic security is homogeneous or not doesn't really apply to them, because they are one singleton. There is no sharding in them. And therefore they don't also suffer from fragmentation. And as we see, all the other approaches that we have talked about, except for JAM, the last one, with an asterisk, because it's, you know, it's like, it's still in, you know, it has the option to not be persistently fragmented, not that it's not all the time. Anyways, too much detail. All the other rollup models, they do suffer from this persistently fragmented downside. The sharded multi-chain, the Cosmos model, is it economically secured? Yes, although it's by nature less secure than, you know, something like the cynical rollup model, or even the optimistic rollup model, or it's basically, it is secure, but it's by nature less secure than all the other things we have discussed. The security is not homogeneous in it, and it suffers from fragmentation. Optimistic rollups with fraud proofs, they are economically secured, because in the presence of frauds, everything should in principle be executed by the L1 validators, and therefore it can be considered to be fraud. It suffers from some downsides, from like long time to finality and so on. And although depending on the implementation, in a world where all rollups of an L1, all L2s of an L1 are, for example, optimistic rollup with the same fraud-proof mechanism and same degree of credibility, we could argue then the economic security is homogeneous. But in practice, what we see in Ethereum and L2s right now, it's not the case. Optimistic rollups without fraud proofs, as I mentioned, I don't really consider this, I consider this to be a non-starter, because to me, it defies the purpose. I think it's missing out on all properties of why we're building these systems to begin with. And these applications probably are better off being, you know, non-blockchain applications, simply put. SNARK-based rollups, they are secure for the same reason of what was mentioned here. They could or could not be homogeneous depending on the network in which they are deployed. What we're seeing in Ethereum right now is that they're not homogeneous, but they can be in principle. Cynical rollups, they are economically secured, and because of this cynicalness and this proactiveness, they are by definition, or, you know, no matter the network where they are deployed, homogeneous in their economic security, but they do still suffer from fragmentation. And finally, JAM is a model that I'm arguing here could perhaps hit all the three axes, in that it's economically secured because it builds on top of the cynical rollup, and similarly it's homogeneous in its economic security because cynical rollups, and it's not persistently fragmented, so it doesn't necessarily suffer from the same issues. All right, closing thoughts. So what we see here is that we are developing different approaches to make this computer go faster. And I believe it's very important to take a step back and look at the properties that they have and how each of these scaling solutions are working in order to come up with the best answer to the question, to the ever more important question of what can we build on top of this computer. So really the main question is which application is best suited for which of these scaling solutions. And that's something I want to leave you with after this talk. Perhaps again, it could be something that I would need much more time to formulate an answer to myself, and I would eventually publish in my blog or Twitter or something. Also worth noting, again, I expressed some opinions clearly in this talk, but broadly speaking, I tried to keep it very, very unopinionated. But I do have stronger opinions, and should you wish to know them, you can come talk to me afterwards, and I would, of course, share them. All right, that's it.